In this video, we will demonstrate the methodology of antenna measurement using a variation of the Purcell reflection method. To begin with, we'll go over a little bit of the historical background for its application. The original method, which was developed in the 50s, was employed to measure horn gain or any antenna gain by processing the difference between the reflection S11 with and without the mirror. That was an acceptable methodology unless the antenna itself experienced a finite mismatch. Later, it was modified to include mismatch. When looking directly into a mirror, the antenna under test sees its image in equal distance on the other side. The reflection of the antenna interacts as a mismatch so that the S11 can be seen to have a variation. This variation manifests itself as a variation in the true gain. Next, let's examine the data and the mathematical formula involved with this method. In this graph, the slope of the line is the true gain of the amplifier versus the distance from the aperture. We can see that the reflection from the mirror modulates the true gain profile in a most interesting way. This was established long ago by Professor Wu. Later, it was expanded and approximated to the following gain formula. The vector difference between the measured S11 with the mirror and the S11 in free space, the magnitude of that vector difference, times the usual constant's 8 pi distance over wavelength, divided by 1 minus S11 free space, or essentially the available gain. This was found to be a reasonably accurate approximation to the exact equations. It should be mentioned that compared to time domain, the direct measurement requires very few frequency points, even a single frequency, and narrow or wide band. So, any antenna can be measured provided cross-polarization is not an issue. Now that we have an understanding of the historical application of this method and the formula involved, let's begin to perform a measurement utilizing the mirror method. First, we proceed directly into the data processing area of the Antenna Measurement Studio software. Now we load the original measurements made on the DE726 horn, which are located in the advanced data directory and are named Purcell mirror measurements.dat. We then invoke the simulator and load the pre-configured schematic file named calculates Purcell's mirror with mismatch correction.sch. As you can see, it's telling us here that Reg 1 contains the S11 data and Reg 2 contains the S11 data in free space. For this processing, the math icon was programmed with Purcell's equation. Here we see it as the square root of the magnitude of register 1 minus register 2 times 8 times pi times L divided by WL divided by 1 minus the mag of Reg 2 squared. We use the square root because the DAMS is all linear. L is the internal variable for distance of the path, while WL is the wavelength. We will now invoke the monitor plots, which allow us to observe the data. We recall the S11 data from Reg 1, and we can see the effect the mirror has compared to register 2, which is the free space measurement. The information regarding the gain of the horn is contained in the difference of these two measurements. Next, we'll generate the path loss at 0.5 meters from the horn phase center to the mirror. We'll then calculate the S21. We need to rescale the plot from 0 to 30 so we can see the DE726 horn profile. We also notice a considerable amount of variation as was originally present in the original analysis. Those variation widths between these points represent multiple reflections inside the chamber from the mirror to the horn. Those multiple reflections can be filtered, and techniques have been developed to perform that type of filtering. The Diamond Engineering Data Filter icon can be used. The data filter icon is a fourth order filter which processes by groups. If we take 20 frequency points at a time, we can go ahead and reprocess the data, and we see that the data error has been largely eliminated. We can take a bigger number of data points and reprocess. what we can see is that we've oversmoothed the data. Some of the known variations are now smooth. Choosing the proper number of points requires some user experience. I'm going to go ahead and use 30 points. Here we can see the horn's natural variations along with the small degree of error. Now we have a fairly accurate representation of the horn. If we wish to use this data and other antenna measurements as a reference, we could export this data as a .s1p file in dB format. A S1p file can be processed in the reference horn section. This enables your own calibrations in your own reference antennas, may it be narrowband, broadband, a few data points, or even just a single data point. And this concludes our overview of the Purcell mirror method and the built-in simulation schematic. We hope you found this useful. Should you have any questions or comments, please give us a call or email us. Thanks for watching.